Happy Easter, chemistry nerds. A little bit of humor to start us off. Happy Easter, chem nerds. So today we are going to be talking about what happens when we collect a gas, but we do it underwater so we can trap that gas in a tube and it won't leak out. So if you remember Dalton's law, which you see below down here, Dalton's law says that the pressure total is equal to the P1 plus the P2. So all we've done here is say when we're collecting a gas over water, we have something called the barometric pressure, which you saw in number 7 on your mixed gas laws homework. And one thing that you need to know is that the barometric pressure is always going to be your P total. The barometric pressure is what the weatherman tells you. The 29.82 inches of mercury, the 30.06 inches, depending on what the weather's like outside. I would bet if we check the weather today, we're going to be 29 point something because we've got this terrible weather on Easter. Tomorrow, it's supposed to be 80 degrees. You're in luck. So we've got this barometric pressure. If you remember back to Dalton's law, we said that the air pressure was made up of several things. So we said that the pressure of the air was equal to the pressure of the water vapor in the air plus the pressure of the nitrogen in the air plus the pressure of the oxygen in the air plus the CO2 in the air, yada, yada, yada. And so this air pressure is made up of a lot of things. It is our total. Well, if we're doing a gas calculation and we want to know the gas pressure for our gas law, we really want this number here. We don't really want this total pressure. So how do we find this? Well, we have to take all of these other things out of play. So the good news is we're not going to be using anything with all of these factors. So this is kind of your new formula for when you see collected over water. You're going to have the P total, which is equal to the gas pressure, which is what you're looking for. And then you've got this water pressure, and I'll explain what that is in just a second. And that's equal to your barometric pressure, your P total, or sometimes they call it the room pressure. So I found this diagram that I thought would make a lot of sense. When you look at this experiment, what they're doing over here is they're heating up some potassium chlorate, which is exactly what we did the day of the gummy bear sacrifice. And we heated up some potassium chlorate. And what that does is it releases oxygen. Well, in this case, we put a tube at the end so that gas had to come down this tube and up under the water and through this bottle. When we put this bottle in, kind of like the day we did the big rocket for the mole rocket, we had to submerge the Coke bottle under the water, fill it totally to the top with water. And so if the whole thing is filled with water and we start bubbling in gas, since the gas is lighter, it's going to float up to the top and it's going to push this water down. So the water gets forced out of the container while the gas bubbles start floating up and filling up this space. So you've got some oxygen gas up here. Here's the tricky part. This up here is not pure oxygen gas. If you remember, what's this water doing? It's sitting here at room temperature. You know that if you leave water out for a week, eventually it's going to evaporate and it's all going to go away. So that's exactly what's happening here, is that this water is starting to evaporate also. And so there's little water vapor molecules mixed in with the oxygen gas. So if the oxygen gas were the red bubbles, which are kind of sad excuses for bubbles, and the blue dots were the water bubbles, and so you've got two kinds of gas mixed up there. So what we would call this whole zone right here would be my P total, or my P room pressure, or my P barometric pressure. So that's everything that's collected in the top of that jar. Well, if we're doing a gas law calculation and we just want to know about the oxygen gas, down here, this would be the pressure of the gas, the oxygen. The water, I'll show you how to find that in just a second. And the P total is the room. And so let's say the P total for today, it was 758 millimeters, since the weather's so yucky outside. It's a little less than normal, which is 760. We want to know the pressure of that oxygen gas. So we have to know what is the water pressure, how much water vapor is pushing on my oxygen up here. Well, we also have to know the temperature. So if we said that the room temperature today was 23 degrees Celsius, that's really close to room temperature. We're going to look at that chart that you've been given on the top of your collected over water notes, and I've just clipped out a portion of it here. And I go over here to 23 degrees and find out when the air is at 23 degrees, the water has a pressure of 21.1 millimeters. So that number is going to go here, 21.1 millimeters. So see if you can follow me. The room has a pressure of 758, which means this bubble up here of gas in the top of my jar also has a pressure of 758. There are two things inside that jar. There is oxygen gas and there is water vapor gas. Well, I've got to get rid of the water vapor because it's ruining my oxygen number. So if the water vapor is 21.1 millimeters of mercury, we're going to solve this for X by subtracting. So we're going to subtract both sides by 21.1 millimeters. This will go away. And we find out that the pressure of the oxygen gas ends up being 736.9 millimeters of mercury. Not stressing over sig fig since I just made up all those numbers. So something around 737 millimeters. So again, all we had to do was get rid of the water because it was adding pressure to our gas, and we can't use that in another law until we get rid of that. Let me show you what this really looks like. Look at example 1 in your notes. You've got some zinc metal reacting with hydrochloric acid to make hydrogen gas. They want to know what is the pressure of just the dry hydrogen, opposed to the wet hydrogen that's got the water vapor in it. So we set this up. P total is equal to the pressure of the dry gas, which in this case was hydrogen, plus the pressure of the water vapor. So we look at our numbers, and they've given us 745 millimeters was our barometric pressure. That's our air pressure. That's going to go here. We're looking for the pressure of the hydrogen. And so now we've got to find the pressure of the water vapor. So if we go back to our chart, we find out that the temperature up here was 22 degrees this time, a little colder. So we look up and say at 22 degrees, the pressure was 19.8. So we're going to plug that in for the water vapor. Now, this chart is only in millimeters, so if they give you atmospheres, kilopascals, torr, you're going to have to convert before you're allowed to subtract. So because both of these units are in millimeters, I'm able to subtract. So we're going to solve this for the pressure of the hydrogen by subtracting the 19.8 millimeters of water vapor. And when I do that, I find out with sig figs this time that my answer is 725 millimeters of mercury. And that is the pressure of my hydrogen, or the pressure of the dry gas. So basically, we just took our water out of the picture. So what does this look like in a real problem? Here we go. Last one. In example 2, here's what you've got to be looking for. It says a sample of gas is collected over water. Your brain has to just catch that. So when you see collected over water, you say ding, ding, ding. I've got P total is equal to P gas plus P water. Ha, she said P water. So that's how I abbreviate all of that. You can even go one step further. P total is equal to P gas plus P water. So there's your formula. We're going to plug things in. The total pressure is 745 millimeters. Pressure of the gas is, I have no idea. The pressure of the water, we'll have to look at our handy dandy chart again. And we're going to find out that this time we are at 25 degrees Celsius. So a little warmer this time. Here we are, 23.8 millimeters of mercury down here. That's my pressure of my water. So we're going to subtract from both sides. And we're going to find out that the pressure of our gas is equal to 721 millimeters of mercury. Oh, but wait. I didn't even read the problem, because when I saw collected over water, I knew I had to do this step. So now let me keep reading. A sample of gas is collected over water at a pressure of 745. Here's the deal. When you see that, you're so tempted to put P1 right here, but you can't. Because of the collected over water, this is really the P total. And so our 25 degrees is still our temperature 1. Our 2-liter volume is still volume 1. And then it says what would happen to the pressure inside if the volume was changed to 1 liter. There's your V2. The temperature rose to 30 degrees. There's my T2. And it wants to know what's going to happen to the pressure. There's my P2. So at this point, you should recognize that you're about to do the combined gas law. The problem is you don't have a P1. In the problem, they gave you a P total. So when we did all of this, okay, here's the take-home message. When we did all of this, the P gas becomes your P1. That is the biggest deal ever. You need to star it, highlight it, do something, call your attention to. When you see collected over water, you're solving for P gas so it can become your P1 in the combined gas law. There's another law we're going to learn later this week called the ideal gas law, and it only has one P for pressure, so in that instance it would become P. But you cannot use the total pressure. You cannot use the 745. It will ruin your problem. So now we continue like normal. We've got the combined gas law. P1 V1 over T1 equals P2 V2 over T2. You know me, I'm going to cross multiply and make it linear. P1 V1 T2 equals P2 V2 T1. I am looking for P2. So I need to solve. Get P2 isolated. Notice I have not plugged in any numbers to this yet. I promise you my way is faster. Try it out. So pressure 2 is equal to, I plug in my numbers. My P1 is my new number that I calculated, my 721 millimeters. My V1 is my 2 liters. My T2 is my second temperature of 30 degrees. When we add our 273, we get 303 Kelvin. Now we've got to put some V2 on the bottom. My new volume was 1 liter. Now think about this. We just took the container and cut it in half. What should that do to my pressure? You should know without me saying. And then my temperature 1 was that 25 degrees or 298 K. So there was a slight difference in temperature, not too big, a huge change in volume. So we should see a pretty decent change in this pressure. Crank that out into our handy dandy calculator, and we get the new pressure is 1,466. Since I love sig figs so much, it is 1,500 millimeters of mercury. So that's that. The only thing you can't forget is collected over water. This is P total. Find that P gas so it can become your P1 in your combined gas law. That's it. Happy Easter. Stay tuned for a joke